Hello everyone and welcome back. So now let's try another example of a system where we can reduce everything to a single equivalent resultant force. Now there's three cases where you can do this: concurrent, parallel, and coplanar. In this case, they're not concurrent, they're not at the same point, they're not coplanar, they're not all in the same plane. However, they are parallel. Since they're parallel, we can put them all at the same point, or we can put the resultant force at a single point and have it have the same external reaction or same external effect on the system. Not internal effect, just external effect. So how are we going to do this? Well, first we're going to find our force, which won't be too hard to do. Then we're going to find our moment, which is a little more difficult. We have to do a few cross products. And then finally, we're going to find the location of that single equivalent force by finding first the y and the x components. We're going to do that separately. So pause here, go try it on your own, and then come back and see what you did wrong or see what you did right. So 3, 2, 1, and there we go. So let's try it out together. The first thing isn't too difficult. We have three forces, all pointing in various z directions, so I just add them together. This gives me my resultant force. Be very careful if you're writing out the k as the direction, because I always want to read that as kilonewton and it's newton. Second thing is we take some cross products, which luckily for us, this isn't going to be too terribly hard. Now, we've got to figure out what the moment is going to be, or we're going to move it to, or we're going to move all of these to the origin. Okay? Move all of them to the origin. So, for the 100 Newton force, I'm going to move it 3 meters in the I direction. So 3I costs 100k. Luckily for me, don't have to do a cross product because there's only two components. It's more or less just a scalar approach, just being fancy. The second one is I have 500 newtons in the k direction, crossed with 4I plus 4j. And you're like, well, wait a second, why would we do cross products here? Well, think about it. Not because you don't need to. You can do a cross product if you want to. In this case, it was just simpler for them to say, okay, well, this is going to cause two moments, one in the I direction, one in the j direction. So I'll just do it rather than writing out the cross product. You still could. It's just, in this case, it's simpler because there's only one component in this force to just multiply it out as a scalar approach, just done twice. And then finally, the 400 newtons moving in the j direction. So I have all of these, multiply them out, and you see that I've got j components and I components. When I add all of those together, I get my resultant moment. Now, using this resultant moment, I can figure out where this one force could be applied to have that exact same resultant moment. So I do the y and the x components separately, but the force is just the same force each time. So negative 1700, that's the y component, over the force gives me 2.13 meters. And negative 3600 over the force gives me 4.5 meters, which tells me there's a point right here, roughly, where if I applied this, it would have the exact same external effect. Now you see that's not even on the board here, so it wouldn't really work very well in this case. But I could have, if it was a little bit longer, applied it there and had the exact same external effect. So, with that, we've done another example. Hopefully it's starting to really click in. If not, we've got some group problem to do, and we'll try those together as well. I'll see you then. Bye-bye.